Hello everyone. This video is to discuss different asymptotic notations used in algorithm analysis. So the asymptotic notations are certain notations which are used to represent the performance of an algorithm. By performance we mean the running time and the memory space used. So these are the three basic asymptotic notations, that is the big O notation, big omega notation and big theta notation. So these notations enable us to represent the performance of an algorithm in a standard way, and these notations will also help us to compare two algorithms in terms of memory space and the running time. So we will look each of these representations one by one. So the first one is big O notation, and it has to be pronounced as big O. The big O notation is defined as the big O of g of n. That is, if you want to write big O of some function, these functions are functions of n, that is the size of the input. So big O of g of n is equal to f of n. So big O of g of n is a function f of n such that there exist positive constants c and n0 such that 0 less than or equal to f of n less than or equal to c into g of n for all n greater than or equal to n0. So this may seem as a complicated definition, but it is rather simple. And if you take it in another words, when n is larger than or equal to a value n0, if the function f of n is always less than c into g of n, then f of n can be written as big O of g of n. Okay, and this notation gives the asymptotic upper bound of a given function. Suppose that I have a function f of n, and if you wish to write this f of n as big O of some other function g of n, then the value of f of n should be less than or equal to some constant, that is some positive constant, into g of n. And we do not want this equation to be always true, but we want it to be true if the value of n is greater than or equal to a specific value n0. And if the function c into g of n is always greater than f of n for n greater than or equal to n0, then we can write f of n as big O of g of n. Okay, we are saying that this notation gives the asymptotic upper bound of a given function is due to the fact that we are taking the value of n which is greater than or equal to n0, that is we are considering the value of n as a bigger value, so that is why the term asymptotic comes. We are saying it as the upper bound because c into g of n is always greater than f of n, so we can say that c into g of n is the upper bound of the function f of n. And let's look at an example. Now we have to check whether n square plus n can be written as big O of n square alone. If we want to write n square plus n is equal to big O of n square, then we have to prove something, and that is we should be able to prove n square plus n is always less than or equal to c into g of n for all values of n greater than or equal to a specific value n0. And we will look at whether we can prove this one for a positive value of c. Then if it is true, then we can write n square plus n is equal to big O of n square. So let me make some space over here. So we know that n is always less than or equal to n square if n is greater than or equal to 1, right? That is, a value will be always less than or equal to its square if the value is greater than or equal to 1. If the value of n is less than 1, then n will be always greater than n square, because if you have a value 0.5 and if you square it, then you will get 0.25. So this squared value is always less than its original value. And if the value of n is greater than 1, then this condition is true, that is, a number will be always less than its square value. Now suppose that I am adding n square on both sides, so I can write it as n square plus n is less than or equal to n square plus n square for all n greater than or equal to 1. Then I can write further as n square plus n is always less than or equal to 2n square for n greater than or equal to 1. Okay, so if you compare this equation and this equation, you can write the value of c equal to 2. So we have proved that n square plus n is less than or equal to c into g of n for n greater than or equal to n0. In this case, c is equal to 2 and our n0 is 1. Okay, because for all value of n greater than or equal to 1, this condition is true. And you can verify the same from its graph. So this is the graph for n square plus n, and this is the graph for 2 into n square. This is where the value of n varies. After the value of 1, you can see that 2n square is always greater than n square plus n, or n square plus n is always less than 2n square. So this condition is true. So I can definitely write n square plus n as big O of n square. That means a constant c into this n square will be always greater than n square plus n. So c into n square gives the upper bound for n square plus n. And we will also say that big O notation is useful in representing the worst case of an algorithm. Worst case is the case by which the time taken by the algorithm will not exceed the worst case scenario. So this function, that is the function inside the big O notation, a constant into that function will be always greater than our function f of n. In order to elaborate that point, suppose that the time complexity of an algorithm is given as big O of n square. It means that the runtime of that algorithm is always less than or equal to some constant into that function n square. So c into n square for some positive constants c, and for all n greater than or equal to n0. Basically, we are trying to convey a message that the algorithm may take cn square time in the worst case, but never more than that. Okay. So this is the idea of the big O notation. To make the drawings general, suppose that these are my axes. So this is how the value of n changes, and you have a graph for f of n. Suppose that this is the graph for f of n. So let me write it as f of n. And you have another graph c into g of n. So let me say that this is c into g of n. And you can see that after some point n, so let me call this one as n0. After the n0, the value of c into g of n is overtaking the value of f of n. So we are defining this relationship only after a value of n which is bigger than n0. Then if this situation happens, then we can write the function f of n as big O of g of n. Okay, so this is all about the big O notation. Now let's turn our attention to big omega notation. And big omega is defined as a function can be written as big omega of g of n if there is a function f of n such that there exist positive constants c and n0 such that 0 less than or equal to c into g of n less than or equal to f of n for all n greater than or equal to n0. In other words, where n is greater than or equal to n0, if the function f of n is always greater than c into g of n, then f of n is big omega of g of n. Suppose that you have two functions f of n and g of n, and if you are able to write the value of c into g of n as always less than or equal to f of n for some value of n greater than or equal to n0 and for some positive constant c, then we can write some function f of n as big omega of g of n. Okay, that means that this notation gives the lower bound of an algorithm. The lower bound means a constant into the function g of n will be always less than my function f of n. So let's look at an example. We have to check whether 5n square can be written as big omega of n. So if at all if you want to write something in this way, then you will have to prove that some constant c into n is always less than or equal to 5n square for some positive values of c as well as some n greater than or equal to n0. These functions values should be always greater than 0. So we are considering the values of these functions which are only positive. If you want to prove that, we can write n square will be always greater than or equal to n for n greater than or equal to 1. This is a true statement. That is, n square will be greater than n if the value of n is greater than or equal to 1. And if you multiply the left hand side with 5, then I can write it as 5n square will be always greater than or equal to n, because you are multiplying a positive value with 5, so that value will be definitely greater than or equal to n. So if you compare this equation and this equation, then you can find that these two equations look similar. So you can write the value of c is equal to 1, that is the coefficient of n. So here in our case c is 1, And if you want to find the value of n, then n will be 5n greater than or equal to 1 or n greater than or equal to 1 by 5. Okay, so which means that for a value of n greater than or equal to 1 by 5, the value of 5n square will be always greater than n. So this function n is the lower bound for 5n square. And if you look at the graph also, this is the graph for n and this is the graph for 5n square, and you can see that after the value 1 by 5 or 0.2, the value of 5n square is always greater than the value of n, which means that the function n is a lower bound for the function 5n square. The function n is an asymptotic lower bound for the function 5n square, and we are using the term asymptotic because we are considering the value of n which is greater than 0.2 and the value of n can go to infinity. Whatever the case may be, this relation will be always true. So this function n is an asymptotic lower bound for the function 5n square. So we can write definitely 5n square as big omega of n. So some points, big omega is used to represent the best case of an algorithm. We are saying best case because all other case will be always greater than the best case. So the best case will be lower than the usual case. So this lower bound function can be used to represent the best case of an algorithm. And in order to explain that, suppose that time complexity of an algorithm is omega of n, then it is conveying that the algorithm is going to perform in c into n time. In our case, c is 1, c into n time in the best case, but never less than that. So the growth function of our algorithm will never be less than the lower bound function. So that is the idea about big omega notation. In order to generalize the diagram, let me draw a picture over here. So this is my y-axis, this is my x-axis. Along x-axis I am writing the value of n. Now first I am drawing the function f of n. So suppose that this is my function f of n. Then I am drawing another function, let's say c into g of n. So this is my function f of n and this is c into g of n, and this would be the value of n0. So for all value of n which is greater than n0, the function c into g of n will be always less than the function f of n. Then I can write this one as f of n belong to the category big omega of g of n, just like our example 5n square belong to the category big omega of n. Okay, now let's turn our attention to the last one, that is the big theta notation. The definition of big theta notation goes like this. We can write something as big theta of g of n if we have a function f of n such that there exist positive constants c1, c2 and n0 such that 0 less than or equal to c1 g of n less than or equal to f of n less than or equal to c2 g of n for all value of n greater than or equal to n0. In other words, when n is greater than or equal to n0, if the function f of n is sandwiched between c1 into g of n and c2 into g of n, then f of n belong to the category big theta of g of n. This notation gives the asymptotic tight bound of a function. That means that if you have a function f of n and you have another function g of n, and if you are able to write c1 g of n, that is a constant multiplied with g of n, is less than or equal to f of n is less than or equal to c2 into g of n, that is if the function can be plotted between c1 into g of n and c2 into g of n for all values of n greater than or equal to n0. This notation gives the asymptotic tight bond of a function, and we will discuss this term very soon. So we have a question here, is n square by 2 minus n by 2 equal to big theta of n square? That is, can we write n square by 2 minus n by 2 as big theta of n square? If at all we want to write this equation, then we have to prove that c1 n square, that is c1 into g of n, less than or equal to f of n, that is n square by 2 minus n by 2 less than or equal to c2 into n square. So first we will look at this side. That is, we can definitely write n square by 2 minus n by 2 is less than or equal to n square by 2. That is, we are taking a number, squaring it and dividing it by 2, then you are subtracting the half of the number, that will be definitely less than this value. Okay, so this is true for any value of n which is greater than or equal to 0. So if you look at this one, then you can definitely write this one as n square by 2 minus n by 2 less than or equal to 1 by 2 into n square. So we have proved the right side, that is you can have the value of C2 equal to 1 by 2 for n greater than or equal to 0. Okay, so we have the value of C2 is equal to 1 by 2, and now we have the value n greater than or equal to 0. Now we have to prove the left side also. So in order to prove this side, let me clear this off. If I focus on the left side, I can write n square by 2 minus n by 2 greater than or equal to n square by 2, and this equation is always true even if I subtract n by 2 into n by 2. What does this mean? If I have a term n square by 2 minus n by 2, that term will be a larger term compared to n square by 2 minus n by 2 into n by 2. Here you have a value, then you are subtracting a quantity, and here you have the same value, you are subtracting the square of that quantity, then this term will be always less than this term. Okay, and this will be true only if n by 2 is greater than or equal to 1, otherwise this number will be a lesser number compared to n by 2. So you can see that n should be greater than or equal to 2. And if you simplify this equation, then you can write n square by 2 minus n by 2 is greater than or equal to n square divided by 4. So this is n square by 2, this will be n square by 4. So the resulting term will be n square by 4. So you can write this one as n square by 2 minus n by 2 is greater than or equal to 1 by 4 into n square. That is, the value of C1 is now 1 by 4. Okay, so you can have the value of C1 equal to 1 by 4, and from this side of the equation you can see that the value of n should be greater than or equal to 2. That is, value of n should be greater than or equal to 2. So we can conclude that when the value of n is greater than or equal to 2, this entire condition holds, and the value of C1 is 1 by 4 and the value of C2 is 1 by 2. If you want to get an intuitive look at the graphs of these functions, this is the function n square by 2 minus n by 2, and this is the function 1 by 4 n square, and this is the function 1 by 2 n square. So you can sandwich the function n square by 2 minus n by 2 between 1 by 2 n square and 1 by 4 n square for all values of n which is greater than or equal to 2. So you can definitely write n square by 2 minus n by 2 as big theta of n square. So this function, that is whatever function you write inside the theta notation, in this case it is n square, will be pretty much similar to the given function n square by 2 minus n by 2. And if you multiply that function with a constant, then that function is less than the original function, and if you multiply the same function with another constant, then that function is greater than the given function. Then you can say that this function, that is n square, is acting as a tight bond, or that is looking similar to the original function given. So you have to notice that we are referring to the same function g of n and g of n over here. It is not like we have two different functions, we have only one function. And to sum up, if an algorithm is performing big theta of log n, suppose that if the performance of an algorithm is given in terms of theta of log n, then in reality the time taken by our algorithm will be between c1 into that function and c2 into that function, but never less or more than that. Okay, that is, we are sandwiching the performance of our function between two constant multiplication of the function given inside the theta notation for any n greater than or equal to n0. So we are basically stating our algorithm is bounded by the function log n. Okay, and the big theta notation can be used to represent the average case of an algorithm. Okay, now in order to sum up this discussion, let me draw some generalized diagram. Suppose that this is my y-axis, this is my x-axis, and here we are varying the value of n, and suppose that this is my f of n. So this is f of n, this is c1 into g of n, and this is c2 into g of n, that is, this is c1 into g of n, and this is c2 into g of n. Then if this is f of n, then we can write the function f of n belong to the category that theta of g of n. Okay, I hope these notations are clear. Thank you.